I'm going to address the learnings that we have had this semester on cosmology. Basic contents are, we're going to talk about two big issues, but the first one particularly is broken into a number of subtopics. It's really about cosmic microwave background. There's a simulation that is included, and then we're talking about the properties of the universe, and there are a number of calculations related to determining those properties. And then there's a bit of a sort of a prognostication on the history that is coming. And the last big chunk is on Big Bang nucleosynthesis. By the way, that's not related to the baryonic heavy model, but it's here for purposes of understanding what the calculations that have been made now come into agreement with observations. So this is a visualization of the simulation that we used. In this case, it's set for the current universe's density values for normal matter, dark matter, and dark energy. This is the version that I'm proposing, which sort of on the play on words that I had in my subtitle to this presentation is I've downplayed dark energy considerably and replaced it mostly with normal matter and a little cut down version of dark matter. So things that are note here on this simulation page is you'll note that even though it's very heavily baryonic matter, it's still considered to be a flat universe. And notice here we see that the power spectrum has been pushed out to about 0.6 degrees. That's important for later. Side by side, you'll see here that the intensity of the peaks and valleys in the CMB are very intense, actually, which I believe is related to the increase in the density of the baryonic material. That's because, of course, the baryons can interact with each other in various ways, whereas our actual universe is very heavily densified with dark matter and dark energy. And if you assume that they can only interact based off of gravity, then you understand why there might be higher concentrations on the high side and the low side where there was a lot of baryons around. This is the comparison of the spectrums. Here I had to resize it in order to fit because if you noticed in the previous slide, it had been chopped off under normal settings. The amplitude here, of course, is intense. I put that into comparison similar to, since this is basically a plot of a sound wave, that if you hit a piece of wood with a hammer, you get a dark thud and almost no harmonics or overtones. And if you hit a piece of steel instead, you get a really sharp ping, and then vibrations continue at a much smaller scale. So I'm thinking that that's probably why we see that. And as I mentioned earlier, the power spectrum has been off-shifted over to the right. The normal universe, the benchmark universe, our universe is over around 0.7 degrees, and this one is around 0.6 according to the simulator itself. So I'm thinking that it's putting a little bit of more of an edge toward being on a negative curvature, but it hasn't really gotten there. So the baryon photon ratio is important to understand because it gives us a great idea of how things are in that plasma that exists right after the Big Bang. And using various equations, we can calculate both the energy of the baryonic, the energy density of the baryonic piece of the universe proposed, as well as the number of baryons per cubic meter, and then the proportional thing between baryons and photons. This is then comparing the baryonic universe to the benchmark model. We can see that the factor of the baryonic heavy universe is about 10 times higher in baryon representation than is the benchmark value. So how does that work out? Well, obviously, when you multiply the number of baryons by 10, so it went from 0.5 in the current real universe, the benchmark, to 0.5. So it went from 0.05 to 0.5. That's a 10 times factor, so it makes sense that the ratio of baryons to photons would have increased by 10 since we didn't do anything with the radiation density per se. Another factor that's important to understand is the temperature of recombination. That's just before things happen with the CMB. In this case, we know that the plasma that makes up the content of the Big Bang is really high temperature, and after the Big Bang, it starts to cool. Eventually, the average energy of photons gets too small to keep the baryons from combining. And once that happens, then the photons don't have to interact with the baryons, and they begin to escape from the plasma. This makes it transparent. The temperature of that recombination process can be calculated, which we do here. In this case, the original value is a little high, and we know from our classwork that the Saha equation calls for it to be factored down by about 0.5, so we end up with a temperature of recombination around 4,200 Kelvin. Comparing this temperature to benchmark, which is 3760. So even with a density that's 10 times high, the temperature increase is only about 8%. That's interesting. Other factors that we need to consider to look at include the redshift and the scale factor. As we know by definition, redshift is how red light becomes when objects are receding from us. The scale factor is a measure of the change in that recession. We've got equations to relate the two, to equate the redshift to the temperature. And in the case of the benchmark here, we know that the current temperature is about 2.7 Kelvin, and the redshift is around 2435, and the value of the scale factor about 4 times 10 to the fourth. Comparing that to the baryonic at these numbers, we can see that they're not off by any factors of 10. They're in the same order of magnitude, I should say. In both cases, both of these numbers, both of the redshift and the scale factor. So it's interesting that it's more or less a factor of 2 rather than a factor of 10 that I might have thought. So in this new universe, is dark energy important? Of course it is. It's a flat universe, and at some point, lambda, capital lambda, dark energy begins to dominate. At the point of equilibrium between matter and dark energy, there's a point we have indicated here, and we can use that point then to calculate the scale factor and the reddening factor for both the benchmark universe in that case and ours. And we'll see here that there's a substantial difference between the two, and also sort of a strange fact that the reddening is a negative value, which I'd like to explain a little bit here. It's easier to visualize in this table version. So what I am presuming that the scale factor being here and the baryon pushing it all the way up to here is related to the fact that this becomes negative. And my model that I have created, which we'll talk about in a few minutes, indicates that it's the equilibrium position for the benchmark was several billion years ago. And in the case of the baryonic model, I'm saying that at the current time, it is not yet occurred. So that's why we get this counterintuitive result. In order to understand the situation a little bit further, I've taken a moment in time when matter fully dominated the expansion of the universe. And specifically, this, by the way, these times are measured in Hubble time. So I've taken 1/10 of the current Hubble time as a point where matter was dominating the mechanics in the universe. That's far from the moment when matter and radiation were at equality, and it's much before the moment when matter and dark energy will be at equality. So again, we've got this possible calculation for that moment when it's strictly matter dominated. That gives us one value. And just for safety's sake, I used another equation which calculates when matter and dark energy share the field. It comes up with not far different an answer. So in this particular case, at that particular time, the redshift is about 3.17 compared to, of course, a zero redshift in today's value. The expansion rate H is the derivative of A over A. And since for matter, it's related to the scale factor is related to time with an exponent of 2/3. We can calculate the first derivative, which will eventually give us all of the information that we need about what leads to the curvature, which is here. So the first derivative is 6.5, which means, of course, that's about 1/10 of what the Hubble constant is today. The critical density here just shows you sort of more makes sense that it's representational of the fact that baryonic matter is 50% of the density of the universe. The curvature situation is such that since we forced the lambda and the omega 0 to be 1, then this, of course, becomes 0. And this leads to this vector, which indicates the curvature to 0, so the universe is flat. Comparing this to the simulator also told us the universe that we were creating was flat. Of course, there's no curvature, so therefore there's no radius of curvature. The second derivative, which we calculate here, of course, turns out negative, and that's also something that we would expect for a flat universe. So in summation, this matter and time that I have selected for my baryonic heavy universe looks like this in summation. These are all factors that are relevant to the equations that we've just seen. To give us some idea about where the universe is headed, I took this graphic from the textbook, which bases the time when radiation is dominant with just this is an indication of a slope that's based off of t to the 1/2. This is off of a slope that is t to the 2/3. Whoops. And this portion of the curve is, of course, based off of an exponential. So I recreated this in a mathematical model. So this part that's in this larger red rectangle is representative of this entire piece, and I just extended it out on time and front and back just so I could see where things were going on the longer term. This is specifically for the benchmark model, just as sort of a comparison to show that this model, mathematical model, was similar to the represented model in the text. And then this benchmark I repeated here to compare to what happens when I put the parameters for the baryonic heavy universe into that same model, and we get this representation. Biggest things to notice, well, there are a couple. The current values are very similar, very close to each other, but this model, since dark energy is playing less of a role, lags behind in this extreme upward shift of the A value over time. So that makes sense as well. This is just a representation of my model, and these are the primary equations in deriving the A values that are characterized in there. There's another graphic that was taken from the text, just shows all of the various curves that universes could take in their expansion, depending on whether they had positive curvature, negative curvature, or were flat. This is the location of our baryonic heavy universe. It's right there at the same spot, more or less, that our actual universe is. But of course, if you were living in that universe, if you were a cosmologist living in that universe, you wouldn't really know without observations which one of those paths it was going to take. So we have observations. This representation shows a collection of observations that actually coincide very accurately with the density calculations for our current universe, which is lambda is about 0.7 and the total matter is about 0.3. So it's right in the middle of that intersection of all of those observations. Our universe, the baryonic heavy one, of course, is sitting off down here with 0.5 on the 0.6 on the total matter size compared, and 0.4 on the lambda side. So if you're that cosmologist without data from your own universe, you won't have a clue about where the universe is ultimately going, except that you know that it's a flat universe. Okay, the last thing I wanted to talk about briefly is Big Bang nucleosynthesis. We want to understand something about helium abundance because we know that there are some unrealistically high densities of helium in the universe, and there has to be a reason for that. So just a brief explanation. At the start of the Big Bang, of course, we know that temperatures are extremely high. Because of these extremely high temperatures, there's ready photons with very high energy available to turn neutrons into protons and vice versa. So there's a rough equivalence in their number at the very beginning. As the temperature continues to cool, protons become to be favored due to their lighter weight. It's harder for a proton to turn into a neutron because it requires a more energetic photon. So photons begin to take over. This is an expression that allows us to calculate the ratio of neutrons to protons at the point as that continues to cool, because we know at a point of about 0.8 MeV of K with the representation of KBT that there is a freeze out of neutrons. That is, that no more neutrons are coming from protons, and so that's the maximum amount of neutrons that you'll ever have in sort of a steady state basis. So there, it's a 0.2 calculation, which works out, of course, to be 1 to 5. After that point, because free neutrons decay in about 15 minutes or so, the neutron level continues to decline just through this natural decay process, which is represented here. And we know that nucleosynthesis begins about 340 seconds after the start of the Big Bang. At that point, the temperature of the universe is cool enough for nucleons to bond. Excuse me. At that point, the ratio of neutrons to protons is about 0.1277, which is basically 1 in 7. So with the temperature set for nucleosynthesis, neutrons and protons begin to form helium. Since the neutron ratio is 1/7 from the previous calculation, we can calculate the maximum possible population of helium, since helium needs 2 protons and 2 neutrons at about 0.25 of the baryonic matter in the universe. So this in turn has been confirmed by modern observation, and since it's so much higher than what we could have assumed being produced strictly from stellar fusion engines, we now have confirmation that nucleosynthesis in the Big Bang was responsible for the actual density of helium that we observed. So we have some theories about the universe. Those theories are supported by observations and the behavior of the universe as it is today. Those observations also and theories also give us some understanding of how the universe will continue, but there is a lot more to come. Thanks for your attention.